All right, I'm going to discuss a problem that involves computation of the magnetic dipole moment of an electron inside an atom. The problem is stated like this. The angular momentum of the electron is known. The angular momentum is known. And we would like to express the magnetic dipole moment in terms of this known quantity. The other quantities that are given are the charge and the mass of the electron. Right. So that's actually a very standard calculation. It's not even a problem. It's part of the perhaps a section. We are going to find that these two different quantities, the angular momentum and the magnetic dipole moment, they are proportional to each other. And then using this, I'm going to discuss some related phenomena. All right, so let's immediately go to solving the problem. So this problem is sufficiently two-dimensional so that I can draw this picture in 2 dimensions. So all the vectors in 3 dimensions, I can show it with a simple notation. All right. Let's remember that there is a proton or a nucleus, a complicated nucleus at the center. We don't care about it. So we have an electron which rotates around this nucleus in a circular orbit like that. The radius of the orbit is given. The speed is given. We are not interested in the relationship between the speed and the radius and things like that. We just know that the angular momentum expressed in terms of these quantities is the given quantity. So let's remember the expression of the angular momentum. Let's remember that the angular momentum is the moment of momentum. So it's position cross the momentum. And the position is, by convention, of course, we choose the origin to be at the center in here. So as a result, that's actually a very intuitive choice. Momentum is mass times velocity, so therefore we can write this thing down as mr cross v. All right. So this is the relationship of between the vectors. I can express this in terms of the magnitude. So let's remember that in the cross product, we have these two vectors which make a 90-degree angle with each other. So since the sine of the 90 degrees is equal to 1, the magnitude of the angular momentum vector is mrv. Right? We say that the magnitude is mrv, and the direction is, this is quite easy to see. I'm going to show the direction in here. The direction is pointing out of the screen, and its magnitude is mrv. All right, let's just write it down like that. And then since I'm going to use the space for other calculations, I'm going to erase these calculations that we have done. Then we have the magnetic dipole moment. So the magnetic dipole moment is equal to current times the area. Area is a vector in here. Let's remember that there is a choice involved in there, but for the direction of the area and for the direction of the current, I can choose them in any way I want, but I would like to choose a direction where the current is positive. Let's just draw the circle again. So this is the same circle, except that now the current along this direction, in the direction opposite to the velocity, is positive. Right? So as a result, with this choice, the area vector is pointing into the screen. So area is into the screen. So therefore, current times the area, therefore the magnetic dipole moment should be pointing into the screen. So I'm going to write it down in here. So magnetic dipole moment is a vector which is pointing into the screen in here. So once we determine the direction, I will then determine the magnitude now. So the problem is the computation of the magnitude. Right? Let me erase these details. So I know that the area is, this is the area of this circular loop. So therefore this is equal to pi r squared. And all I need to compute is the current in here. All right. Computation of the current might be confusing because we don't have a steady current in here. We have a single particle which is rotating around. right? So as a result, if you remember the convention for the definition for the current is the amount of the charge that crosses the given surface divided by the unit time. So let me then do it like this. So as a result, we need to choose some kind of a surface in here, an imagined surface in here. And we would like to think about the process where the electron crosses that surface to the other side. Actually, the motion of the electron is like that. The electron goes like that, but along that direction, a negative charge passes. So for each crossing, of course, the charge crosses from this side to the other side is positive. So therefore, the current is positive along that direction. Let's remember this. So what we do is, even though the electron is discrete, it's just a single particle moving around. So we don't have a steady current which is continuing. If I consider a long enough time, I can compute an average current in here. So what I need to do is to consider a very long time and count the number of times the electron crosses this yellow surface in here. So let me write number of crossing in here. So the charge of the electron with a positive value times the number of times that the electron has crossed that surface in this time divided by the time gives us the value of the current. But that's very simple if you just consider one period. So therefore, in that case, the number of crossing is 1. The period is a very short time interval. But of course, since the number of crossing is proportional to the time interval, I can just compute this ratio for one period, and in that case there will be one crossing. So therefore this is charge divided by the period. Let's quickly compute the period. This is circumference divided by the speed. So therefore this is EV divided by 2 pi r. Right? Now I'm going to erase something more. Once I get an expression for the current, let me erase this and then continue from here. Then magnetic dipole moment has a magnitude, which is current times the area. Current is EV divided by 2 pi r. This is just a positive number. Let's remember this. Area is pi r squared. So therefore we get EVR divided by 2. So let me write this thing down in here. EVR divided by 2 is the magnetic dipole moment. Right. Again, I'm going to erase some of the details in here. Right. But I'll keep working on this expression. What I do in here is to divide this expression by the mass and multiply with mass. Why? Because in that case I get the magnitude of the angular momentum in here. So therefore the magnetic dipole moment is equal to E over 2m times the angular momentum. So we don't know the speed, we don't know the radius of the orbit, we just know the magnitude of the angular momentum. So as a result, we write the expression like that. All right, let's remember again that both angular momentum and the magnetic dipole moment are vectors. Now we just found the relationship between their magnitudes in here. But we also have found the relationship between their directions. So angular momentum is pointing out of the screen. Magnetic dipole moment is pointing into the screen. Right? So we also know the direction. So therefore, I can write this relationship down vectorially. So therefore, I would then say magnetic dipole moment is equal to minus E over 2m divided by the angular momentum. Minus because they are in opposite directions, and the rest is just the equation that we have derived for the magnitude. So again, let me erase everything else in here. Right, that's the answer to the problem that that has been asked. Angular momentum is given, the charge and the mass of the electron is given, and what's the dipole moment? So this is the expression of the dipole moment. Right. So At this point, I'm going to discuss the magnetism of atoms by using this expression alone. So the nice thing about this expression is that these two different physical quantities are related with some constant in here, and this constant has a nice feature. It just depends on the charge to mass ratio of the electrons. So that magical ratio in here appears also in here. What is nice in here is that this ratio is the same for all electrons. So that's called the gyromagnetic ratio. That's equal to, basically this is the charge of the electron, which is minus E divided by 2 times the mass. So we can also write the same relationship for other charged particles as well. If we had a positively charged particle, in that case the magnetic dipole moment and the angular momentum would be parallel to each other. But since the electron is negatively charged, they are anti-parallel. So the minus sign is actually coming from the sign of the charge. Let's just keep this in mind. What does gyromagnetic means? Gyro is related with the angular momentum. It's basically a word meaning rotation. All right. Magnetic as well is the magnetic is the word that actually corresponds to this magnetic property. So especially the magnetic dipole moment. So it kind of tells us that this magnetic property and the rotational property are proportional to each other. They have a fixed ratio, and that ratio is minus E over 2m. So that's why we call this as the gyromagnetic ratio. So what does that constancy of the expression in front, the coefficient in front, this ratio mean? It means that if an atom has not just a single electron, but many electrons, so one electron has an angular momentum L1 and the other one has L2 and so on, many electrons in there, in that case, the total dipole moment of the whole system, which is obtained by summing the magnetic dipole moments of all the electrons, can be expressed as this ratio, which is the same for all electrons, plus the sum of the angular momenta. Which means, of course, I can then say that the same expression is valid for the total angular momentum. So, as a result, this relationship is valid, but it's also valid for the case where we talk about the total angular momentum of all the electrons, and this is the total magnetic dipole moment of all of these electrons. So they are always proportional to each other with the same proportionality constant and the same relationship. So this basically tells us that if I have an atom that has an angular momentum, which is coming from the electrons, then this atom should always have a magnetic dipole moments. All right, that's a very general rule. You can safely use it everywhere. So then let us just discuss some of the other issues. So one of them is this: why do we call this as a dipole? So let's remember what dipole means. Di means two, pole means pole. So that essentially means this thing has two poles. And the question is, where are the poles? We didn't see it in here because we haven't discussed this, because this issue has some other related to some other magnetic, some other phenomena. This magnetic dipole moment, we have introduced this to describe the interaction of the atom or whatever that physical system is, a current distribution, with an external source of magnetic field. So there are some other, let's say it like this, external moving charges in here that produce a magnetic field. They produce a magnetic field. We introduced the magnetic dipole moment to describe the interaction of this system with the magnetic field. But that essentially implies that this system actually interacts with these external charges, right? So it's actually an interaction between two moving charges. But of course, these moving charges are not simple. They are complicated current distributions. But I can describe the effect, the interaction in the other way around. So I can actually think that this dipole in here produces a magnetic field, not this one, right? Not this one. I'm erasing this one now. I'm describing the magnetic field produced by my system by the yellow color in here. This produces a magnetic field, and these external charges are interacting with this yellow magnetic field, right? So as a result, there are actually, you can think of it, there are two magnetic fields produced. One is produced by these external charges, and one is produced by my system. So this basically tells us that this magnetic dipole in here can also be thought as the source of magnetic field. So let me erase these. So this is a source of magnetic fields actually. So we are going to make this description a little bit more precise in the next chapter when we talk about when we compute the magnetic field produced by charges, by current distributions. The magnetic dipoles are the sources of the magnetic field. So as a result, I can think of them, now I'm going to erase all of these yellow things and the external charges. I can think of this atom in here with a magnetic dipole as a magnet. And this is actually the source of all magnets. So we know that the magnets have poles. There is a north pole and the south pole. And we just define the poles as somewhat a region, that's the magnetic dipole moment vector, a region which is around the tip of the magnetic dipole moment as the north pole, and the region around the toe of the vector as the south pole, right? We don't have a we don't have a precise place for the poles. We just describe a wide region as a pole in a way. We can think of this as some kind of a pole. So as a result, we try to describe it like that. In the case of electric dipole moments, we can precisely associate the poles with the locations of the charges. There's a positive charge and a negative charge in there. So we can identify where the poles are exactly, and we can also associate a point for that. But for a magnetic dipole, we cannot do this, because in the case of magnetic dipole, we have actually a current distribution. Let me show it like that. There's an electron that kind of, let me choose the direction of the velocity in the opposite way. So the electron is rotating like that, all right? So that corresponds to a current which is flowing in the opposite direction, which corresponds to a magnetic dipole moment along that direction, right? So in this picture, for example, we can associate this upper part of that region, right? It's not a single point, as the north pole, and the lower part of that region as the south pole. So there is some kind of an association in here, and we can think of the atom as some kind of a tiny magnet, right? The real permanent magnets are actually formed from these atomic dipoles. And so as a result, you can think of them as these tiny magnets which are just joined together. But in any case, that's the source of the two poles in here, and that's the reason why we just call this dipole moment as the dipole moment, because somehow we are associating these two poles, north and south poles of magnets, with these. Okay. So after we handle this, let's then pass to another topic, which is confusing. So electron has an angular momentum that we can compute by using its velocity and the position by this formula, right? That's the well-known angular momentum of the electron. But it appears that the electron also has an internal angular momentum, which is always present, even though the electron is not moving, even if it is at rest. When it is at rest, of course, the orbital angular momentum would be zero, but there will still be this additional internal angular momentum. We just call this as the spin, right, or the spin angular momentum, but in short for spin. We use it with, we show it by the capital S symbol. So it's just an angular momentum. Let me just say it like this. So if we want to compute the total angular momentum of the electron, I need to add these two. So that's the total angular momentum. And the relationships that we have seen before, the relationship between the torque and the angular momentum is also valid between this total angular momentum and the torque. So the rate of change of the total angular momentum is the torque, right? Just keep this in mind. But the origin, the physical origin of the spin is hard to explain. People usually use this model. Let me erase this. This model where the electron is imagined as a sphere, like the Earth, for example. So this sphere has this translational motion around the atom, just like the Earth has this rotational motion around the Sun. But in addition to that, the Earth also rotates around itself. So as a result, in this model, they imagine that this electron as a sphere is rotating around itself. So as a result of that, this is a rigid body rotating around itself. So therefore, it has an angular momentum, which is given by moment of inertia multiplied with angular velocity or something like that. All right. So people usually imagine the spin angular momentum as arising from the rotation of the electron around itself. Unfortunately, this is not true because this kind of a picture, this model has lots of inconsistencies. There are things like, for example, if you just model the electron like that, then you're saying that the electron has a radius. And when you try to compute the rotational speeds, they find that the speed should exceed the speed of light and things like that. There are these kind of difficulties with this interpretation. So as a result, we nowadays say that the spin angular momentum, we don't know how it arises, but it is due to the internal structure of the electron. Internal structure within quotes, of course, because we always we have said that there is a point particle. A point particle cannot have an internal structure, but somehow electron carries that additional angular momentum. It's called the spin. So when there is spin, what can we say about the magnetic dipole moment? Well, yeah, we also have an additional dipole moment coming from the spin. So we have a dipole moment coming from the orbital angular momentum. There is this, let me write it down, this orbital. There's also a dipole moment coming from the spin. So there are these two additional ones. So we have for the orbital angular momentum, this is we have the gyromagnetic ratio multiplied with the angular momentum. Orbital angular momentum is the relationship between them. For the spin part, spin contribution, we also have the same relationship. That's the charge divided by 2 times the mass multiplied with the spin. But it turns out that the coefficient in front is not that simple. There's something called a G factor that multiplies it, that expression. So for the case of electron, this factor is almost equal to 2. It's very close to 2, so as a result, most of the time people write it down like that. So that's basically ruins everything. So we have a gyromagnetic ratio which is different for the spin part. So as a result, the total angular momentum, total dipole moment for the electron that actually takes into account both the orbital angular momentum of the spin and the spin is basically given by an expression like that, which is not that simple. We would like to express this side as in terms of the total angular momentum, but we cannot. But in any case, that's some kind of a difficulty that the atomic physicists have to deal with. But in any case, the rule that we say about when we say that when there is a total angular momentum for the electrons, when this total angular momentum is non-zero, in general, the total magnetic dipole moment is also non-zero. So these kind of atoms are always magnetic. Right? Just keep in mind. Then there is this protons and neutrons. Do they have magnetic dipole moments? Yes, they have. They also have spins, both proton and the neutron. The neutron is kind of complicated because neutron, we know that it's neutral because that's why we call it as neutron. But it's actually formed from charged particles, we know that there are at least 3 quarks inside. I think 2 of them are negative, one of them is positive, but I forgot which ones. It's charge neutral, but it's formed from charged particles, and so therefore, since these charged particles have their motion inside the neutron and they also have spin, somehow the neutron also has a spin angular momentum, and as a result it also has a dipole moment, a magnetic dipole moment. And if I remember correctly, the magnetic dipole moment was opposite to the spin angular momentum of the neutron. For the case of proton, of course, the angular momentum, this is actually spin in here. It's not the orbital angular momentum, but in any case, they are in the same direction. There's a complicated G factor in here. We have to multiply this with a number which is close to 4m5, but I forgot again which value is the case. So as a result, for protons and neutrons, we can also talk about these magnetic dipole moments as well. So when we talk about the magnetic dipoles, magnetic properties of matter, there are 2 possible contributions. Electrons have a contribution, but the protons and the neutrons also have a contribution as well. And so in general, of course, the atomic nuclei have these dipole moments. So as a result, there is also a nuclear contribution. But what is interesting in here is that the gyromagnetic ratio for the proton involves the mass of the proton. And for the electron, of course, we have the mass of the electron in here. And we know that the mass of the proton is about 2,000 times the mass of the electron. It's about 1,800 times. It's very large compared to the electron. This is some kind of an unnecessary detail at this point. It turns out that these angular momenta of the electrons and the protons, they have the same order of magnitude. That's around like 10 to the minus 34 joule seconds. So as a result, since the angular momenta have the same size, but we have a mass in here, it appears that the magnetic dipole moments of the protons are always much smaller compared to the electrons, which means, well, you can neglect them. So magnetic dipole moments of the protons, in general, the nuclear magnetic dipole moments is about, let's say, 1/1000, because there are also these G factors as well, times the magnetic dipole moments of the electrons. So when you're talking about a magnet, for example, you can safely ignore the magnetic dipole moments of the protons. So they don't have any effect at all on the magnetic properties of magnets. So when we talk about the magnets, their magnetism actually comes from the electrons. So either the orbital motion of the electrons around the atoms or their spin degrees of freedoms. And most of the time, the spin degree of freedom is more dominant, usually. All right, so let me just quickly say that the protons and nuclei in general have magnetic dipole moments. And this NMR spectroscopy, nuclear magnetic resonance, is actually how we couple to the nuclear magnetic dipole moments of the atoms. So somehow we apply a magnetic field which is changing with time and which somehow adjusts the frequency appropriately so that this magnetic field directly interacts with the magnetic dipole moment of the nuclei. So the NMR spectroscopy is actually uses that coupling. All right. There's one last thing. I'm sorry about this. Let's say that you have a magnet. This might be an iron bar, a magnet in here. It's just a magnet. Any kind, doesn't matter. There's a north pole and the south pole in here. I can think of this as actually a magnetic dipole moment. I can model this as a magnetic dipole moment. This magnetic dipole moment is actually a sum over atomic dipole moments. All right, just think about it. So by adding the atomic dipole moments, we get this large dipole moment, and we can describe the magnet as a macroscopic matter that has a total magnetic dipole moment which is non-zero. Okay, so next, let's remember that in the case of atomic dipole moments, the atomic dipole moments are associated with the angular momenta. So there's a let's just write down this gyromagnetic ratio in here. So each atomic dipole moment is proportional to the angular momentum of the atom. So therefore, it seems that, of course, this magnet is somehow associated with some kind of an total angular momentum, which is just a sum over the angular momenta of each atoms. So as a result, when you take a magnet in your hand, well, this magnet has a dipole moment, so therefore it actually has an angular momentum. You don't notice this because you don't see any rotation, but it indeed has an angular momentum. But this angular momentum is somehow hidden. You don't notice its effects, but it is there. So that's kind of strange, because you don't see any motion, but still this matter has a mechanical property that is associated with the motion. So the reason why you don't notice it, because the rotation actually happens inside an atom. So there's a rotation inside the atom, but there's no macroscopic rotation of this big object in here. There's no macroscopic rotation. So that's the reason why you don't notice it. And here there's an interesting experiment in here. We can do these kind of experiments. So suppose that you have a cylindrical bar magnet like that. There's a north pole and a south pole. You just hang it with a wire, and you just make sure that it comes to rest so that it doesn't move anymore. So we don't notice it, but since there's a magnetic dipole along this direction, there is an angular momentum. But this is hidden, so let me write hidden in here. There's an hidden angular momentum. So suppose that we have done some experiment where somehow, by applying some external magnetic field, by using electromagnets, we can do this. We switch the positions of the north and the south poles. It's not easy to do with yourselves by using magnets, but in the labs we can do that. So we just place them inside some electromagnets. If we just apply a sufficiently large magnetic field in the opposite direction, we can switch the places of this north and the south pole. Right? In which case the magnetic dipole moment changes direction, which means that the hidden angular momentum also changes its direction. All right? That's kind of interesting, because you can also do this process without applying any torque on the magnet. So as a result, this implies that because of the conservation of angular momentum, somehow the initial angular momentum in here should become equal to the final angular momentum. This implies that therefore this thing actually starts rotating, and it should start rotating along this direction, right? This is the rotation direction, where there's an angular momentum associated with this. So that's the angular momentum of the bar, right? So that's called the Einstein-de Haas effect. All right? It basically tells you that the angular momentum associated with the bar magnet is somehow hidden, but using this kind of an experiment, you can make it visible. So somehow this change in the direction of the magnetic dipole moment therefore becomes associated with the macroscopic rotation of that bar magnet. So that's kind of a clear indication of the source of the magnetism of macroscopic matter.